All right, I think we're recording. So yeah, welcome everyone to week 9. Hope you guys are having a good morning. And today we're going to be looking over a lot of basic heart stuff, just sort of start you guys off for cardio, and then also looking at some of the back and spine stuff, as well as some medicine of the mind. Let me just open the chat. Perfect. All right, let's dive into it. So the very first thing that we're going to be doing is having a look at the heart in general. So we just want to get an idea of how the heart works, because we're going to be exploring a lot of stuff about the specifics of the cardiac anatomy and the physiology, and that requires at least a basic understanding of what the heart is and what it does. So the heart is one of your most important organs. It pumps blood throughout your body. And you can sort of think of it as having two major parts. So one is the right side of the heart, and one is the left side of the heart. Both of them receive blood from somewhere and pump the blood to somewhere else. So the right side of the heart receives blood from your veins, and it gets deoxygenated blood because it's coming back from your body after the oxygen has already been used. The left side gets oxygenated blood from the lungs. So the right side takes it from the body and sends it to the lungs. The left side takes it from the lungs and sends it to the body. Why do we bother doing that? Because the lungs are where we get the oxygen in order to supply the rest of the body. Each of those sides has an atrium, which is where the actual vessels come in. So on the right side, you have the superior vena cava and the inferior vena cava. They come into the right-sided atrium. On the left side, you have the pulmonary veins. And on both sides, you have then a ventricle, which pumps stuff back out. So on the right side, you have the pulmonary trunk, which takes stuff to the lungs. And then on the left side, you have the aorta, which takes it to the rest of the body. So the key thing to understand there is that the two systems are sort of semi-independent. And by the time we're in the adult circulation, it's very important that we have separation between those, and that we keep the oxygenated blood and the deoxygenated blood both separate and well organized. Now, that's not actually the case in the fetal circulation, which we'll see in just a second. And so a lot of the embryology of the heart is how we get from a very simple heart structure to a relatively complex one that you see here. Another thing, we have little valves. So the valves between the atrium and the atria and the ventricles, they're called the atrioventricular valves. The valves between the ventricles and the vessels that they go into, so the aorta and the pulmonary trunk, they're called the semilunar valves. All of those are one-way valves too. So they don't let blood go back the wrong way, because that would disrupt your circulation, basically. We can have a lot of problems if blood goes back the way it's not meant to go. So we're going to cover this in more detail next week when we do cardiac anatomy more broadly. And we'll also do a little bit more about circulation later today when we go through physiology. But this is the basics for now. Don't worry too much about getting it down perfectly. This is just to orient you a little bit. Okay. So let's look at how we actually form this, and where we're going to be, what we want to get to is we need to turn the fetal circulation into the adult circulation. The adult circulation, like I just told you, the right and the left heart are very separate, okay? So things come into the right heart, they go to the lungs, they come from the lungs, they go to the aorta via the left heart. Those need to be kept separate because we don't want to mix oxygenated and deoxygenated blood. But in the fetus, the lungs don't do anything, right? Because the fetus is in the womb. There's no way for it to get oxygen in except through the placenta, I should say. So the fetal circulation needs to allow external blood to come in and do the work that the normal oxygenated blood from the lung would usually do. But it also needs to have a structure that can be very quickly adapted to the adult circulation, because once the baby is born, you need to be able to then shut off those two sides and stop moving between them. So the way we do that is we have a whole bunch of shunts. A shunt is basically just a shortcut. It's a hole somewhere where in the adult circulation there is no hole, and it allows things to spread. So the overall path for the fetal circulation is that you have oxygenated blood coming from the mother through the placenta. There's the first shunt, which is the umbilical vein. It then goes into the inferior vena cava. So usually they'd be carrying deoxygenated blood, but in this case, it's carrying oxygenated blood that will go up into the right atrium. We then don't want to waste time going through the lungs because they don't do anything. So we have a shunt called the foramen ovale, which goes directly from the right atrium to the left atrium. So that way, oxygenated blood can go straight to where it's needed, which is the left atrium to the left ventricle, to then be pumped through the fetal circulation. Okay, so that's the general idea, is that we want to get the shortest path possible for oxygenated blood, which means not mucking around in the right side of the heart as much as we can avoid it. These are some of the general shunts. I've mentioned two of these before. So the foramen ovale, so that's a one-way valve. It allows blood to go from the right side of the heart to the left side of the heart, for reasons I've discussed there. We also have the ductus arteriosus. So that is a different one. I haven't mentioned that yet. Basically, although we have that shunt, that shortcut between the right side of the heart and the left side of the heart, some blood still goes into the right ventricle because there's a valve there. We can't shut that off. Which is a good thing because we want some of the blood to go to the lungs. The lungs are still living tissue. Even though they don't work, they need to be kept alive, okay? So the ductus arteriosus is a connection between the pulmonary trunk, which is that Y-shaped sort of thing coming out of the right ventricle here. Keep in mind, right and left will always be flipped because you talk about it from the patient's perspective. So the ductus arteriosus is between that big Y-shaped pulmonary trunk and between the aorta. So that allows us to take all of that blood, which was meant to go into the circulation because it's oxygenated, and put it back into the aorta where it's actually useful. The ductus venosus is sort of linked to the pulmonary, not the pulmonary, umbilical, I can't speak today, sorry, umbilical vein to allow blood to come from the placenta and into the fetal circulation. Yeah. I put a little adult thing there, so that means basically the remnant in an adult person. So two of these become ligaments, so they sort of close up and they get what we call obliterated, which basically just means that they fill in with ligament tissue and they're no longer open, because it would be very bad if we had deoxygenated blood mixing with oxygenated blood. Yeah. Okay. So in terms of the very basic, like initial formation, we originate from the mesoderm near the neck. So the heart actually starts up quite superior in terms of the fetal orientation, but it slowly gets pushed downwards until it reaches its position in the torso. So that's why you have, say, the diaphragm being innervated by the cervical nerves, despite being very low. Like the diaphragm is the level of thoracic vertebra, but its innervation comes from all the way up here. And that's because it started up here and it went down there during fetal development. That also has a clinical impact in terms of referred pain. So because the innervation comes from up here, you can get referred pain in a heart attack to lots of stuff that is also innervated by C3, C4, C5, for example. And so that's why you get referred pain all over that general area rather than, where the heart actually is. Okay. So this is the basic form of the heart. Okay, so this is what we start out as, and it is very, very primitive, as you can see. It's basically just a long tube. It has a bunch of inflows. So it's the sinus venosus. Remember, that's going to be bringing in oxygenated blood from the outside. And then we have the primitive actual heart. And then we have the bulbus cordus and the truncus arteriosus, which take that oxygenated blood out. So remember, in the adult circulation, this whole thing is a big machine to pump deoxygenated blood and oxygenated blood. In the fetal circulation, all it needs to do is get the oxygenated blood from outside and pump it through the body. So we need to go from this to the adult heart. This doesn't look very much like the adult heart, so we're going to need to do some things. First, we're going to need to fold it, because as you can probably tell, the atria are meant to be on top of the ventricles, and they're currently the other way around. Something needs to be done about that. And we also need to separate it, because right now it's just one big sort of chunk. Okay, it's one big tube. We need to separate it into other chambers, because the adult heart has many different chambers that do different things. Okay, so our first step is folding. I don't know if this is useful, but I always thought of it as like someone like hanging over one of those gymnastic bars. You can see like the two aortic roots over there. It's like the legs over the bar, and they're sort of like pulling themselves up. They have a lot of core strength. They're pulling themselves up and around. and wrapping around the bar at the top. So the ventricles, they start above, but they grow faster than the atria. And that plus some general movement means that they eventually push down. So if you look like, if this is superior, this is, sorry, if this is, wow, I can't remember today. So this is the front of the patient, this is the back of the patient. It starts like this and it curves up behind. So like the diagram shows, the atria are actually going to wrap up around the back of the ventricles to sit on top. They don't come around the front or to the other sides, they come around the back and then sort of loop over. There are other diagrams on future slides that will explain this a little bit better. So the outcome of that is because we folded it like that, pretty much everything comes out of the top. The inferior vena cava is the one exception to that because it comes from the bottom, because it's, well, from the bottom. But everything else both enters and exits the heart from the top because we folded it in two like this, okay? In terms of how, like, the remnants of this that you see in the adult anatomy, so like it says there, the rough parts, the really muscular parts, come from the actual embryological heart, so that blue region, and part of the red region. I don't know why they've changed the color scheme. The smooth parts come from the bulbous cordus and the sinus venosus. So those are the not quite the embryological heart proper. Okay. So the other thing we need to do is septation. So we have just one big tube. This is after we've already folded. So you can see here the little curved sort of curl shape we have now. You can see at the top we have the aortic roots, and then the atria have already wrapped around the back and started looping over the top of the ventricles. But it's still all one big pouch. So even though we've folded it like this and we're starting to look a little more like an adult heart, we still need to actually separate it into different compartments. And so we do this in a number of different stages. So the first stage, you can see the diagram sort of going through the progression, is that we grow what we call the septum primum, so the first septum, from the very top of the heart to the endocardial cushion, which is a little bit of tissue, which is right in the middle of the heart. And so it provides a very useful sort of landmark, and it'll actually do some chemical signaling to signal cells at the top of the heart to start growing down to meet it. There's a problem here, which is that we need to separate the atria in order to prepare for the adult circulation, or the birth circulation, I should say. But we also need to keep a path between them because, like we said, we're still getting oxygenated blood into the right atrium, and we need to shunt it to the left atrium to have an efficient fetal circulation. So we're going to do a really weird thing where we need to both separate the two parts, but also keep them connected. We need to have a path between them. So the way we do that is, first, there's just a gap because there's nothing between them. That's called the foramen primum, or sometimes the ostium primum. Then when we do grow that little septum primum between them, we then have a hole in that. And that's called the foramen, or the ostium secundum. So that's an actual hole. The first one is just the absence of anything. This one, there's a membrane between them, but it's got a hole in it. And then finally, we have the septum secundum, which is a lot thicker than the septum primum. And that's going to grow between them again, but it's going to have another hole in it called the foramen ovale. And so the final form, per se, is the foramen ovale plus the foramen secundum, which sort of combine to form a one-way valve. We'll talk a little bit more about this as we go, but you can see there the difference between image 5 and image 6 there, in the bottom right corner, is that when there's higher pressure on the right atrium, so the left side of the image, the blood is able to force its way through. So it's sort of like there's a hole, there's a hole in something, and there's a piece of paper or something flimsy sort of flapping against it. If something's pushing from this side, then that paper can sort of flop away and let stuff through. But when pressure builds up on the other side, so stuff here, it pushes the paper or whatever the flimsy thing is against the actual hole and covers it up. So you can see there in image 6, when we have a higher blood pressure in the left-hand side of the heart, it actually pushes that foramen ovale shut. And it means that the blood can no longer mix. That's going to become very important after birth. For now, the other thing that we'll look at is the ventricular septum. So we need to also separate the ventricles because they're not one compartment in the adult heart. That one's a little bit more simple, because we don't really care that much about the connection between those two at this point. The one little quirk there that's probably important is that most of the ventricular septum is formed from the bottom and sort of just a big muscular growth that moves up. A little bit of it comes from the endocardial cushion itself. So the endocardial cushion grows down a little bit to meet it. What that means is that the top of the ventricular septum, or the membrane between them, is actually a little bit weaker because there's less stuff there, because the endocardial cushion tissue isn't as robust as the muscular tissue that's growing up to join it. What that means is that when we get a ventricular septal defect, so something's gone wrong in development and the ventricular septum is open, it's usually at the top because that's flimsier. Okay. All right, the last step is our truncus arteriosus division. So as you can see there again, image A is sort of after we've done a little folding and maybe even we've had septation, we can't tell from the outside, but the truncus arteriosus and the bulbus cordis are still one big thing, which is not good because we need eventually to have a separate aorta and a separate pulmonary trunk because those are going to carry oxygenated and deoxygenated blood respectively. We can't have those mixing. So what we actually do is we just form what we call a aorticopulmonary septum between them. So that's it's very twisted, but it forms in that little tube and eventually they separate somewhat and they become two separate tubes. So the aorta ends up a little bit posterior to the pulmonary trunk. Again, don't worry about this too much right now, but when you look back at that overview image, you'll see that each of these semilunar valves, so between the right ventricle and the pulmonary trunk and the left ventricle and the aorta, have three little petals. And each of them will have a right petal, a left petal, and the aorta will have a posterior petal because it's posterior, and the pulmonary trunk will have an anterior petal because it's anterior. But yeah. Okay, this is sort of a summary of all the general stuff. So the top box is more or less the folding step, where we can see how it wraps around from behind and sort of sits that way so that they actually are now located on top of the ventricles. And then the bottom box is septation. So again, you can see how we start with, this is sort of a little bit after we've started, so you can see that there's already septum primum starting to form and an interventricular septum starting to form. At the end there, at 8 weeks, we have a foramen ovale at the top, so that's our final form ready for birth. And at the bottom, we have a ventricular septum with a thinner part near the top. Don't worry too much about the valve stuff, that'll become important later. Okay, so at birth, we actually get the usage of that one-way valve. Okay, so like I said before, when the pressure on the right-hand side, which is the side with the thicker membrane, when that's higher, it means that it pushes the thinner membrane away and lets the blood through. When the left heart pressure is higher or equal, then that pushes the septum primum flat against the septum secundum, which seals the gap and prevents blood from mixing between them. So during the fetal circulation, while you're inside the fetus, the lungs are at quite high pressure because they're not being used. They're just sort of filled with fluid. There's no oxygen going through there. When you're born and when you take your first breath really, your lungs suddenly drop in pressure massively, which means your right side of the heart, which is connected to your lungs, also drops in pressure. And so what that means is that the pressure difference between your right side of your heart and the left side of your heart is no longer massively in favor of your right side. And now the left side blood is going to get pushed against, is going to push against the septum primum and seal the hole. So almost naturally, well, not almost, literally naturally, your body is able to switch right at the first breath when the lungs become useful to the circulation which actually uses the lungs, which is pretty awesome. And then over time, those are meant to fuse because you don't really need them again. So yeah, this diagram, quick note, is not actually the heart at birth. So you can see that the ventriculus septum hasn't actually fused, this is about 43 days, which is much earlier than you'd actually get born, hopefully. Okie dokie. So the last thing we need to look at is what if something goes wrong. So we have different defects with the septum. The atrial septum, you can either have a patent foramen ovale, or there's also primary defects, which are a little bit more, it's sort of just there's a hole. But the patent foramen ovale is much more common and much more high yields, basically. It comes up more often on exams. So in a patent foramen ovale, you get failure of the septate to fuse, and then you get backflow of oxygenated blood to the right atrium. So that's because the left side pressure in the heart is still going to be higher. So we never end up getting deoxygenated blood into the left side of the heart because the pressure difference is just too much in the left side's favor now. But we do instead get left-sided oxygenated blood being forced back into the right side. Excuse me. The split S2 sound thing is going to make zero sense until you learn about cardiac sounds a bit later, so don't worry about that too much. We also get what we call a systolic murmur. You don't need to know too much about that again, except that a murmur is sort of a disturbed heart sound. So usually the blood rushes through your heart very sort of orderly. A murmur is when we get some sort of disturbance in that. So there's something disrupting the heart sort of flow. And in this case, it's because there's blood going the wrong way, basically. So that's just an indication that something is going the wrong way or pushing against something or otherwise weird. In terms of, those are clinical signs, so stuff that you actually know once you examine a patient. In terms of symptoms, so things the patient might notice themselves, you can get shortness of breath, you can get fatigue, and you can get swelling of the lower body, usually. So this sometimes spontaneously self-resolves, so they'll just fuse by themselves. So sometimes you'll just monitor a child with an foramen ovale and just see if it fixes itself. If it doesn't fix itself, you might need to do surgical treatment. So the ventricular septal defects, basically almost just because they're further away, they're less important. So they can combine with other conditions to cause more harm, but by themselves, ventricular septal defects are not usually super important, and we can sometimes just leave them be. If we do need to treat them, we usually do it surgically again. So we just put something to patch the hole, basically, in both cases. Okay. And then there's the patent ductus arteriosus. So if you remember back to the shunts I talked about, the foramen ovale was one. We just talked about the defect in that. We've also got a defect potentially in the ductus arteriosus. So it's meant to become the ligamentum arteriosum and gets obliterated again. If that doesn't happen, then you now have a hole between your aorta and your pulmonary trunk, which is pretty bad. So again, because the pressure in your left side heart is so much higher than your right side, and by extension, the pressure in your oxygenated circulation is higher than in your deoxygenated circulation, the oxygenated blood is going to get pushed into the pulmonary trunk rather than the other way around. So basically the blood from the aorta is going to instead go back to the pulmonary trunk instead of going to the body like it's meant to, which increases blood pressure in your lungs, basically. So you can have respiratory issues because there's too much fluid in your lungs. And you can also have what we call cardiac hypertrophy, which is where your heart muscle grows a lot thicker because the heart has to work harder, basically, to pump blood to your body. Because your body's not getting all of that blood because some of it's getting siphoned off into the pulmonary circulation. So what we can do to treat it is that we can, in some cases, use NSAIDs, which actually has to do with the, not embryological, but the post-birth signaling, which is that as long as you have high prostaglandin levels, closure of the ductus arteriosus is inhibited, but naturally, those levels are meant to drop after birth, which signals that to actually close. So if they're still high for whatever reason, we can sometimes use NSAIDs to lower the levels like we would for inflammation, and therefore help fix this, basically. And we can always just surgically correct it as well. One more quick note. So there are 3 shunts I talked about, but I've only talked about defects for 2. That's because the last one, the ductus venosus, is just sort of connecting the belly button, which is where your your connection to the placenta is going to be, your umbilicus, to your hepatic circulation, your liver, and then through that to your superior vena cava. So if that one's still open, it kind of doesn't mean much. It's that might be issues with belly button formation or something like that. And it doesn't do anything much because that is sort of a vestigial structure in the body, because you're not connected to the placenta anymore. So blood doesn't really have any way to mess with the oxygenated versus deoxygenated circulations if that were to stay open. So it's not really as important to us. Okay, final one is a complicated one. So it's called the tetralogy of Fallot. Tetralogy, like tetra meaning four. And we have four combined components, so they all need to happen at the same time for it to be that. So the acronym is like the mnemonic is PROVE. So pulmonary stenosis, right ventricular hypertrophy, overriding aorta, and ventricular septal defect. Okay, so we'll walk through each of these ones in turn. So first of all, we have pulmonary stenosis. So you're going to learn about stenosis. It basically means that instead of like being, easily able to open and close, the valve is sort of stuck sort of half open most of the time. It's very stiff and it's not able to move, which is bad for the right ventricle, because that's the one that needs to push stuff into the pulmonary trunk past the pulmonary valve. And if that's sort of stiff, then it's harder for blood to get through. So there's higher resistance on that path. Right ventricular hypertrophy is a direct result of that. So the right ventricle is going to, again, build muscle because it's working harder. You'll see this happen again and again. We also have an overriding aorta, which means that the aorta is more central, and it's less sort of on its proper side towards the left. It's instead more to the middle, so it's easier for it to get blood from both sides. And then finally, we have a ventricular septal defect, which means that there's a gap between the ventricles. So this is sort of all building up to cause a very particular set of circumstances. And so the deoxygenated blood gets to the right ventricle, then the right ventricle is going to contract and try to pump it somewhere. Now, it doesn't actually want to go up the pulmonary trunk because that has higher resistance because the valve isn't opening properly. So what it does instead, because it can go to the left ventricle, it does go to the left ventricle, or not too much, not necessarily too much into the left ventricle as it is into the aorta. So it's the fact that we have an overriding aorta which allows this to happen more easily, because like I said, the left ventricle pressure is still going to be higher. But if you have an overriding aorta, it's easier for it to just slip in with the blood from the left ventricle, basically. So this is what we call a cyanotic defect, because we end up with like blue extremities, like arms, feet, hands, skin, that sort of thing, because there's deoxygenated blood getting into your circulation. So the other ones, they don't usually cause cyanosis, but this one does. In terms of treatment, we try and fix up the hole between the ventricles, and we try and fix up the valve. So those are the two things we can do. The right ventricular hypertrophy, it can resolve when we fix up the valve, and the overriding aorta doesn't really present a problem in of itself. Okay, and this is just a little summary slide of some other stuff. The important stuff are the atrial septal defect, the patent ductus arteriosus, we talked about them, the tetralogy of Fallot, persistent truncus arteriosus means that the pulmonary trunk and the aorta are not separated. So then you just have massive mixing of the deoxygenated and oxygenated blood. Transposition of great arteries is kind of interesting because it basically just means that they're in the wrong place. So the aorta is where the pulmonary trunk should be, and the pulmonary trunk is where the aorta should be. So stuff is going like the exact wrong way. And so because things are in the wrong place, and that means that your right heart is pumping your deoxygenated blood back into your body, that's also cyanotic. So that can be quite dangerous potentially. But yeah, those are the important ones. Coarctation of the aorta is something else. I won't spend too much time on it now, but you can look at it in your own time. But yeah, that pretty much sums it up. If you guys have any questions, feel free to chuck them in the chat. But other than that, I will hand it off to our next presenter for a quick overview of the physiology side of things.
All right. Good morning, everyone. I'm going to be taking over from here and actually changing perspective a little bit into the physiology of the cardiovascular system. system. So James has done a fantastic job of talking to you about the different parts of the heart and sort of the different parts of the circulation. So you may have some idea now that, we used to think, or like back, heart is just something that pumps blood everywhere and it's just one sort of unified circulation. But now hopefully you have some idea that it's actually sort of composed of two circulations, right? One is specific to every other tissue in the body, whereas there's another smaller circulation which is specifically to the lungs. And I want to develop that further by giving you an overview of the system from a physiology lens, and then going into a little bit about those two different circulations, how they're different, what the different pressures are, etc. So again, if you have any questions, put them in the chat, but we will get started. Okay, so just really quickly before I go into the complex physiology, I just wanted to give a brief overview of what the cardiovascular system is. Again, we already have some idea, but just to give you an idea of what the three major components are, we've got blood, which is the fluid that actually goes through the system. And that's what's, there's obviously many, many functions of blood, but the major function of blood is going to be to carry oxygen to the tissues and then carry carbon dioxide back to the lungs so that it can be exhaled. So that's blood. Then you've got the vessels. So we've got two types of vessels: arteries, veins, obviously like capillaries and other subtypes, but they're just basically the hollow tubes that allow us to carry the blood to the tissues or allow us to carry blood away from those tissues. And then if you really think about it, the heart is just a glorified pump. So all it's doing is it's basically like a blood vessel, but it's been adapted so that it's able to generate the flow that allows every other blood vessel to take blood to tissues and take blood away from tissues. So the major, most high yield point I want you to get out of the slide is that the heart has absolutely nothing to do with emotions. So when people say their heart has been broken, or they say that, I'm feeling a lot of compassion, I feel it in my heart's pumping out of my chest and things like that. It has nothing to do with the emotions. It's just to do with increased flow. Really, all the emotions happen up here. So your heart, if you're ever just thinking about like, what does the heart do? It's just a pump. Now, what are some of the major functions of the cardiovascular system? The most basic function that we are now aware of is that it's to do with gas exchange. So it's taking oxygen to tissues, taking carbon dioxide away from tissues. That's probably the most important function. Alongside those gases, we also get the supply of other types of nutrients, which we'll go into a little bit later, and the removal of waste like acids and things like that. By doing this, it's also going to be able to control the sorts of metabolic activities that are happening in those tissues. So is it supplying a lot of O2 to certain tissues? That means that those tissues will be more active. Is it supplying less oxygen? That means those tissues are going to be more dormant. And that'll depend on the activities or the demand of those tissues, depending on the activity that you're doing. So whether you're exercising or whether you are resting. It's also surprisingly very good with temperature modulation and blood pressure modulation. So if you think about your vessels, if you're going to increase the diameter of your vessels or decrease the diameter of your vessels, again, we'll discuss how this happens in later lectures. That's going to mean that, like, if I dilate them more heat's going to be able to escape from the vessels, which means that I'm going to have a decreased body temperature. So really good for temperature control. And the second thing is blood pressure. So this will be something we discuss when we come to resistance, but the more I dilate my vessels, the less resistance I'll have to flow. The fourth major function is that it's going to allow us to take hormones, immune mediators like antibodies and white blood cells and so on to tissues that are undergoing inflammation or have some sort of pathogen or foreign body that's invaded into that tissue. So that's one really, really important function, which you would have gone over in immunology. And as I mentioned, the heart has nothing to do with love. So that's definitely not one of the major functions of the cardiovascular system. But you knew that already. Okay, now what are the major circulations? So we've already discussed this a tad bit. We've got the pulmonary circulation, which is taking blood to the lungs, also taking blood away from the lungs. We commonly discuss that this is the right side of the heart. And that's more when we're thinking about the outflow. So it's coming out from the right ventricle. It's obviously, like, when you think about it, it's going from the right ventricle into the lungs, but then it's coming back into the left atrium. So when we say right side of the heart, we're thinking about the right ventricle. That's where the blood flow is coming from. It's the more high pressure circuit. And the reason why is because you've got like a smaller length of tubules running through this entire circuit. So that's going to be at 95 millimeters mercury. And you've got high oxygen blood going into the arteries, low oxygen blood going into the veins. In the systemic circulation, you've got the opposite. So it's to every other tissue that you're supplying blood. This is the low circuit one, low pressure one. So it's going to be 15 millimeters of mercury. You've got low oxygen. Oh, I think I may have swapped this around actually. High oxygen. Oh yes, sorry, my bad, guys. I think these 3 dot points are supposed to be at the bottom, and these 3 dot points are supposed to be at the top. So high oxygen blood. So yeah, that makes sense. So systemic circulation, you want high oxygen blood to be in the arteries because you're supplying all the tissues with oxygen, whereas you want the low oxygen to be taken back into the heart and then up to the lungs to be reoxygenated again. So this should be the other way around. I'll correct it, and I'll also add a little message disclaimer in the video on YouTube. But just to clarify things a little bit with regards to the circulation, because we haven't had too much time to cover it. If you just have a look at this diagram here, just to give you a brief overview and to orient yourself. Remember that we start off with the right ventricle and we're pumping blood through the right ventricle into the major outflow trunk, which is the aorta. And that aorta, there's definitely going to be many, many branches that happen here, but this is just a very simplified diagram. It's taking that oxygenated blood through all its branches into the systemic tissues. From there, once all the oxygen is used and all the metabolic activities have been exhausted, that's when your blood now has almost no oxygen or very little oxygen. And all that blood gets carried through into veins and venous capillaries, etc., up to the major trunks known as the vena cavae. So you've got the inferior and superior vena cava, which are taking blood from different parts of your body. That's going to enter into your right atrium. From your right atrium, it goes into the right ventricle. And then from the right ventricle, it enters into the pulmonary arteries. And so this is what I meant previously and where I realized my mistake. The pulmonary artery is actually carrying deoxygenated blood. So it's not necessary when I say artery that it's going to be, red sort of high oxygenation blood. There's actually the exception with pulmonary arteries, which are taking deoxygenated blood to the lungs. So instead of thinking about arteries as things that carry oxygen or a lot of oxygen, think about arteries as things that take blood away from the heart. And then the opposite, veins, will take blood to the heart. So it's just a shift of perspective, but that just clarifies some of the definitions. And then from there, the lungs will oxygenate them by taking in oxygen, coupling it to the hemoglobin on the blood. That's going to take it back through the pulmonary veins. Now they're highly oxygenated into the left atrium and then so on. So it's all a cyclical process. And again, just to clarify, these should be the opposite. So one is high pressure, one is low pressure. And systemic circulation should be high pressure just because you've got many, many more tissues to supply. Okay, and as I kind of went through, you've got a very predictable flow. And the sooner you learn this, so like the sooner you identify what the pathways are, the easier it'll be, especially when you come to anatomy and you discuss, or even physiology, when you further discuss some of the pathologies that can arise if you have problems in any of the ventricles, for example, with heart failure. Okay. There are 2 types of circuits that you will find within each of these circulations. And if you've done any physics before, you may be familiar with these terms. So series circuits and parallel circuits. Before we go into this, just remember that the cardiovascular circulation in a normal, healthy human being should be a closed loop. As long as you don't have any breaks or anything like that, all the blood stays within the vessels and it doesn't go anywhere else. So generally, you would expect that the blood flow should be relatively constant, apart from if you have some dilation or constriction of some of the vessels. So a series circuit is found, or series circuits are found in both the systemic and pulmonary circulations. So if you have a look at this diagram here, you can see that the same amount of blood, if you just follow like the black lines, I know this is a slightly complicated diagram, but it's kind of taking our simplified diagram from here and just like extrapolating it out a bit and showing you that, yes, you've got the right atrium, right ventricle, you've got left atrium, left ventricle, all the blood flowing through from the lungs, but you've also got many, many organs that are being supplied from the left ventricle. In other words, the left side of the heart or the systemic circulation. So it's not as simple as was shown in the previous diagram. With series, we're just saying that, these straight lines are all series circuits, which means the same amount of blood is traveling through each of these lines. So it's an equal amount of blood per unit time. When we come to this point here, when we come from the aorta, and as I said, the aorta has many, many branches that supply different organs, that's when we start to encounter what is called a parallel circuit. So this is where all of that blood is now going to get split up depending on the demand of each of these organs. So you can see that, for example, in this diagram, the gastrointestinal and skeletal muscles are requiring 25% each of the total outflow from the left ventricle, whereas something like your heart itself, so coronary circulation is the blood flow to the heart itself and the heart tissues, requires probably the least, as well as the skin, which is about 5%. So this will all depend on the activity that your body is going through. So this might be in someone, for example, who's undergoing a lot of exercise. You may want a lot of blood flow to the skeletal muscles, but not so much to the gastrointestinal tract, just because you're not really digesting anything at that stage. But the question is, how does it do this? So it's not constantly going to be 15% to cerebral circulation, and then all of these will be fixed. They are always changing. And so that's what we say is like a dynamic circulation, where it's not always going to be constant. It's going to be changing depending on demand. The question is, how does that happen? And that is where we come into the idea of hemodynamics. So the way that we get this parallel circuit to work and the way that we can actually modulate the amount of blood flow to each of these organs. Okay, so that's where we come to hemodynamics. Now, this is a relatively short section because it's actually not that complicated. And I'm hoping a lot of these concepts will be fairly intuitive once you know some of the formulas and know where they come from. The first idea is about pressure gradients. So the key idea I want you to get out of this slide is that blood flow will only happen when there is a difference in pressure across a vessel. And for example, we're focusing right now on arteries, but the same thing will happen when we discuss veins. So the relationship that you want to keep in mind mathematically is that flow is going to be proportional to the difference in pressure. So flow proportional to difference in pressure. Why is this important? Well, if I have no difference in pressure, no matter how high the actual absolute values of those pressures are, like let's say I have 180 on the left side and 180 on the right side, that's definitely going to be quite high, but there's not going to be any tendency for the blood to want to go in any of those directions. Blood will only want to go from high pressure to low pressure environments. And this is a very common theme, no matter where you look. Like even if you look at osmosis, diffusion, things really want to go from places that have high concentrations, high pressures, to low concentrations or low pressures to balance things out. So that's the key theme. Again, if there's no difference, there's going to be no flow. And this proportionality, so this direct proportionality between flow and difference of pressure, is only going to be true if there's laminar flow. So there's two types of flow, right? There's laminar flow and there's turbulent flow. With laminar flow, that's just smooth, right? So like you have no obstructions, the vessels are all patent, there's nothing that's blocking blood flow. So everything is going to be quite direct. If you have turbulent flow though, and this is what James was sort of alluding to when you think about murmurs and there being obstructions, from a physiology perspective, whenever you have turbulent flow, you can actually hear that when you're auscultating on someone's heart or any of their arteries. So when you go into clinical skills and you think about things like carotid bruits, or you think about systolic murmurs, diastolic murmurs, all that really means that something is wrong with the valves within that vessel, or there's something obstructing the blood flow through that vessel. And that's causing noise to occur because the blood is kind of hitting that valve continuously instead of just flowing nicely through. And so this diagram just shows a couple of examples, which you don't need to be familiar with as of yet, but a couple of examples where you may get this noisy turbulence occurring. So here's normal valve that's open, normal valve that's closed. When you have a stenotic valve, that's going to mean that, yeah, blood flow might be able to get through a little bit, but it's going to kind of come backwards. So it's quite narrow, which means that all of the blood is going to be concentrated into one small region where it's trying to flow through. And obviously that blood is going to be kind of frictionating against each other, which is going to lead to a lot of turbulent flow, hence murmurs. And then you've got insufficient valves. So the valves are there to try and, as James was mentioning, keep everything one way. So if it's insufficient, it's going to try and go forward, but then also there's going to be some space for it to come back. And you've got, again, blood hitting that valve continuously, which is not ideal, but that allows us to be able to hear all these noises when we're trying to make a diagnosis, which can be quite useful. Okay, and then the second relationship is to do with resistance. So what are some of the factors that allow us to increase or decrease the resistance within a vessel? So why are we discussing this? Well, if you think back to the diagram, right, of all the different circulations, if I'm undergoing exercise and I don't want too much blood to be going into my gastrointestinal tract, I need to try and increase the resistance of the vessels that are going to the GIT to be able to stop blood from getting there. But then I also need to redirect all that blood into the skeletal muscle circulation. So that is going to require less resistance. So how do I modulate the amount of resistance within each circulation? There are a couple of factors that are involved, but the main theme that you want to be familiar with is that resistance will slow down flow. So the more resistance I have, the less flow I will have. And the key relationship here is flow is equal to delta P. So again, difference in pressure, but now we're adding a new element, which is dividing by resistance. So it's effectively the same thing as this one, right? So flow is proportional to delta P, but now we're just specifying it further and saying we have to divide this relationship by resistance. So this is important because if you think mathematically, increasing resistance will lead to decreased flow, which is kind of what we were saying with the key theme. So what properties affect resistance? There are three main ones. We've got radius, length, and viscosity. Again, if you've done physics, these might already be familiar with you, for you. So resistance is going to be inversely proportional to resistance. Radius is going to be inversely proportional to resistance. So resistance is proportional to 1 divided by radius to the power of 4. In other words, if I increase my radius by 2 times, I would expect there to be a decrease in resistance by 2 to the power of 4, so 16 times. So this is actually the most important factor that's going to be responsible for increasing or decreasing resistance, just because of the relationship, right? It's to the power of 4, which is quite a big change if I was to just cause a small change in resistance. And here is a graph showing you how this occurs. So it's a very exponential relationship. The more I increase resistance, the more I decrease, or the more I increase radius, the more I decrease resistance. Very confusing. But just think about it as a very exponential relationship. For length and viscosity, they're more straightforward. So they're direct proportionalities. So in other words, if I double length, I'll double resistance. If I double viscosity, I will double resistance. So it's very straightforward. And when I say viscosity, I'm talking about the resistance to flow. So anything that's going to cause my blood to become, I guess, a lot more difficult to flow. So it becomes more dense. Like if you think about, if I'm trying to squeeze water through a tube versus if I'm trying to squeeze toothpaste through a tube, the toothpaste is going to be a lot more viscous, or in other words, it's going to have a lot more resistance to flow because it has more density. The same thing happens with blood, but it's obviously not going to be the same sort of thing with water and toothpaste. In the case of blood, you're going to have a value called hematocrit. And hematocrit is just a fancy way of saying the percentage of the blood volume that's taken up by red blood cells. So the blood volume is the liquid, and then the red blood cells are all the solid. So if you have any situations where you've got more solid increasing within your blood, that's going to increase the amount of resistance that that blood is going to have, and therefore increase viscosity. Hopefully that makes sense. And if you have any questions, let me know in the chat. For anyone who's a bit more maths minded and just wants to remember one formula and not have to remember all these 3 different relationships, this is the actual formula that there is for resistance to flow. And this applies to any tube, but we're thinking about blood vessels. We're thinking about 8 times, so that symbol I think is like eta or something, 8 times eta times L, which is length, divided by pi times r to the power of 4, and that eta symbol just means viscosity. So this contains all the relationships that we've just discussed, but kind of specifies it further with all the different actual values that you'll require. So if you want to remember this, by all means, go for it. And finally, this is what I was saying before with regards to the changes or the dynamic part of this hemodynamic circulation. So we've discussed how we can increase resistance, how we can decrease flow. But why is this useful? Because if you look at rest and if you look at strenuous exercise, obviously you're going to have a change in the amount of cardiac output. So in this case, you can see it's almost more than 3 times cardiac output. But we want it to be directed towards organs that are going to be useful for that strenuous exercise. So rather than all of the circulation going to, for example, the abdominal organs, which you might require for rest and digest mode because you've just eaten food, you might now want it to increase to places like the heart to be able to increase that cardiac output, also to the skin to be able to allow for temperature regulation and allow for you to get rid of all the excess heat that your body is generating. And then most importantly, to the skeletal muscles to actually allow you to move. And so your muscles don't just become ischemic and start dying because they require a lot of demand. And here's another diagram just showing you the kind of the specific percentages to each of those organs if you'd like to have a look at that. Okay, and finally, kind of wrapping it up. So we discussed all the different hemodynamic principles, but now let's focus on the skeletal muscles. Sorry, not the skeletal muscles, but the cardiac muscles themselves. How do they actually contract? So what is actually causing them to contract? And then later on, we'll talk about the electrical activities that are happening in the heart, which Jane will talk about. All right, so just as a bit of a preview, remember that in skeletal muscles, you've got a very complicated process happening that's allowing them to contract. And if you think back to semester 1, hopefully you remember that you've got this concept of excitation contraction coupling. Now, in cardiac muscle, it's very much the same. There's just an added layer that's really important to understand with cardiomyocytes as opposed to skeletomyocytes, where you require extracellular calcium for this to occur. Whereas with cardiac myocytes, it's more just straightforward, right? You've got your nerve coming in, acetylcholine, it's going to cause an influx of certain ions and therefore contraction. With cardiac muscle, it's a little bit more different. But those major principles will still apply. So basically, if you want to simplify this down, just remember that your heart is slightly more special than any other muscle that's found in your body because it really requires extracellular calcium to contract. So just having a lot of calcium within the cell is not enough for contraction to occur. And we'll discuss why that's the case through these steps. So with regards to the actual steps that occur, the first step that happens is that calcium from the outside is going to enter into the muscle cells or the cardiomyocytes. And the specific receptor that this occurs through are called L-type calcium channels or L-type calcium junctions. And what that's gonna do is that calcium is gonna come in and it's gonna trigger the release of more calcium from within the sarcoplasmic reticulum of the cardiac cells. So remember, the sarcoplasmic reticulum is basically just the smooth endoplasmic reticulum, which has been modified within muscle cells. So they contain a lot of calcium. So that's like an additional function of those sarcoplasmic reticula. They contain a lot of calcium. That calcium is going to now be stimulated to release from the outside through ryanodine receptors. And that's going to lead to more calcium building up within the cells. So in other words, before I might have had a little bit of calcium within my cell, but now I've got a huge influx of calcium. Now that calcium, I'm not going to go into, so this step here, the contraction, that's what I was saying in terms of contraction or excitation contraction coupling. That should be all revision from semester 1. Remember how, the calcium, you've got myosin, actin filaments, all that stuff still applies. But the main idea I want to get out of here is that this calcium has to be triggered from outside rather than just being from the inside, because you require a lot of calcium for contraction to happen. And then finally, once the contraction has finished, very similar to skeletal muscles, you don't want contraction to be constant, right? You want your cardiac muscles to relax and then contract again to keep on beating. So how that happens is all that calcium now needs to get reuptaken through the calcium ATPase channels. And it's calcium ATPase because it requires ATP to pump the calcium back into the sarcoplasmic reticulum against the concentration gradient. Because sarcoplasmic reticulum has a very high concentration of calcium. The outside has a much larger volume, so has a very low concentration. But I do want that calcium to return back in, otherwise I'm going to have unnecessary contraction and I need relaxation. So to pump it against concentration gradient back into the SR, I need to hydrolyze ATP, in other words, to liberate the energy and then pump it against the concentration gradient. So the main clinically relevant ideas from this is that if I have a very low concentration of calcium on the outside, or if I have a receptor blocker, so if I have something that blocks the calcium channel, this will be something you really, really will discuss in pharmacology, then my force of contraction will decrease. And this might be clinically useful in some respects. And also probably just another idea to keep in mind is that if you think about cardiac transplants or heart transplants, the reason why you can take the heart out of someone and then like put it in like a box and then transport it to another hospital to be able to get the transplant done is because that heart is put into a solution that has a very specific high concentration of calcium. And you can actually see that if you take the heart out of like a frog or something, and there's experiments online you can have a look at, you can actually keep it beating just by keeping it in a very specific solution of calcium and other electrolytes. So that's a very interesting idea. And it just shows you the power of having a high concentration of calcium extracellularly to keep that heart pumping. Okay, now some definitions to understand for later physiology lectures. So it's not so much discussed in these lectures, but you'll come across, for example, I think you may have a practical on exercise and how that affects your stroke volume, cardiac output. So for now, it's just a good idea to get used to what they mean and what the definitions are. With regards to stroke volume, all this means is you just kind of have to look at the units for each of these to figure out what they mean. So stroke volume is liters per beat, and all this is to do with the ventricles and the heart. So how much volume of blood am I ejecting from my heart with every beat of the ventricles, or every beat of the heart effectively? So what determines this? Well, there are two main factors that will determine stroke volume. They are EDV and ESV. So EDV is referring to end diastolic volume. And I'm aware that you probably haven't heard of the terms diastolic and systolic yet, or maybe you have when you've thought about things like blood pressure. So if you think about blood pressure and you look at the numbers, right, you've got a big number and you've got a small number. The big number is systolic, small number is diastolic. Whenever you think about systolic, you're thinking about contraction. Whenever you think about diastolic, you're thinking about relaxation. So when the ventricles have relaxed, there's still going to be a small amount of blood. No matter how small, it's still important. And we'll discuss why having EDV is important later on. You're going to have an amount of blood that's left after the relaxation of the ventricles. Same thing happens with contraction of the ventricles. Not all of the blood is going to be ejected out of the heart. In fact, some blood will actually still remain within the ventricle. The difference between those two values is what our stroke volume is. And that kind of makes sense, right? You've got a certain amount of blood in your heart when it's relaxed. When it contracts, it's going to eject a certain amount of blood. Some is going to be still left over. If you take the amount that was there originally, minus it from the amount that's left now, that's going to give you the amount that was released. So it's very intuitive. So that's what the definition of stroke volume is. So why is stroke volume important? Because it actually influences the total output of your heart, which is what we call cardiac output, or CO. It's very much the same as stroke volume, but instead of thinking about the liters per beat, which might not be so clinically important for us yet, we're thinking about the actual volume released in liters per minute. And so normally your cardiac output should be somewhere between 6 to 7 liters per minute at rest. But when you're exercising, this can increase to quite a bit. So you can see sort of here, with strenuous exercise, you can increase by almost like 3 to 4 times. So 20 to 25 liters per minute. But in trained athletes, it can go even higher. So 30 to 40 liters per minute. The question is, how is this possible? And actually, before I go on further, I just wanted to go back because I've just received a private message. Yeah, so at the top, I wrote calcium-induced calcium release. This is probably a good term to just like know. So CICR is just what all of this means. So you've got calcium that you require from the outside. So that calcium is going to induce the release of calcium within the cell. So CICR is the method that cardiac cells will use specifically. Okay, so what are some of the factors that actually allow us to increase cardiac output? Well, it all comes down to this formula. So if I want to increase cardiac output, I need to either increase heart rate or I need to increase stroke volume, or both. And you can see a sort of trailer of this. When you have a look at this diagram here, there are a lot of factors that are feeding into heart rate, and there are a lot of factors that are feeding into stroke volume. So let's try and dissect this a little bit more in the next couple of slides. So remember this formula. Let's start with heart rate. This is probably the easiest one for us to kind of think about right now, because you'll have a whole lecture on this, and I don't want to tread on the toes of anyone doing this one. But in order to increase heart rate, it's effectively just trying to increase sympathetic innervation towards the SA node and also ventricles atria, and decrease parasympathetic innervation to all those structures, so that we can get greater contraction and greater cardiac output. So that one's relatively intuitive to understand, but you'll discuss some of the other factors that are involved, for example, renin-angiotensin, etc., in another lecture. For now, I want to talk about stroke volume. So how do I increase stroke volume? And this is where I was mentioning why EDV is so important. You can either increase your EDV or you can increase your calcium concentration. So hopefully, before I even discuss any of these, hopefully these make a little bit of sense given the physiology that we've discussed so far. So let's start with EDV. We've got this really interesting mechanism, and one that you should be quite familiar with by the end of today and by the end of your lectures, which is called the Frank-Starling mechanism. So obviously, 2 people, I think, or 1 person, I'm not really sure, discovered this mechanism, and it's been really useful in our understanding of why it's very important for venous return, or why venous return is so important and dictates our cardiac output. So in other words, really just to simplify it down, the mechanism states that the more the ventricle is filled, So the more blood we have within the ventricles, the stronger it's going to be able to contract. So just from a really simple perspective, this probably makes some sense. But from a physiology perspective, if you zoom into the actual cardiac muscle cells, and if you look at the actual sarcomeres, remember that they're composed of the actin and myosin filaments, and the more overlap you have, remember thinking back to skeletal muscle, the more overlap you have, the greater the force of contraction will be. Of course, you don't want too much overlap because then they'll just be counterproductive, but you want a specific amount of overlap to be able to get the greatest contraction out of those sarcomeres. So whenever I have more blood in my ventricles, I'm going to have those cardiac myocytes, or the ventricular myocytes specifically, being stretched out a lot more. And this is going to cause my sarcomeres to lengthen quite a bit. And the more length that I have, if you kind of have a look at this diagram, when they're short, yes, they're going to have a bit of contraction, or at least a bit of overlap. But when I get them to stretch out a little bit more, I'm getting rid of that counterproductive overlap where I've got, overlap on overlap on overlap, which is not really useful. I'm going to be able to separate them out a little bit more so that you can actually see those overlaps more distinctly. And the second important thing about this is now you have a lot of potential space to be able to contract. So the more lengthy they are, when they contract, they're going to cause a huge contraction rather than them being really close at the beginning and then contracting and only causing a little bit of contraction. So the more stretched out they are, the more contraction you're gonna be able to get. And the way that you want to increase EDV is by increasing venous return. So when the blood comes back from systemic circulation, from your head, upper limb, lower limb, pelvis, wherever it is, the more blood that comes through venous return, it's going to increase the amount of preload. And preload is just a fancy way of saying the amount of blood coming in from venous return, goes into the atria, goes into the ventricles. Ventricles dilate a lot more, sarcomeres lengthen a lot more, which means I get more contraction. Now, what's not shown on this graph, so it's a very nice curve showing you that, yes, the more you have at the end of ventricular diastole, so EDV, the more you have, the greater the stroke volume is going to be. So it kind of shows that relationship. But what this doesn't show you is that near the end, if you have too much EDV, this relationship actually drops down. And so that's sort of the unhealthy amount of venous return that you don't want. Again, not too clinically relevant, but just to kind of make you aware that this doesn't continue infinitely. You will have a point where you have so much venous return that your sarcomeres are so have so little overlap because they're so stretched out that really you won't get much contraction happening. So there's a certain, I guess, optimal EDV that you need to be able to generate the most stroke volume. And so that's what this Frank-Starling curve, what we call it, is showing. And then finally, another way you can increase SV, probably the simpler one to understand, is by increasing the actual amount of calcium that you have around the cells. So how do I increase the amount of calcium? Well, the main way that this happens is through my sympathetic neurons. So again, this should mostly be revision from neurology back in semester 1, or some of the stuff we actually discussed in semester 2. You've got your sympathetic neuron, you've got its noradrenaline being released. And what it's going to do is it's going to bind to the beta receptors. So think about the types of beta receptors that we have on the heart. It's usually going to be beta 1 receptors, but you also have other receptors found in less concentrations. It's going to bind to those receptors, stimulate the entry of calcium within the cell, and that's going to lead to our CICR, so calcium-induced calcium release. Now, it's really important to remember, and it's kind of more of a trivia sort of thing rather than it being too clinically relevant, is that sympathetic stimulation only affects, or only sympathetic stimulation will affect ventricular contraction. It's because there's no parasympathetic innervation to the ventricles. Parasympathetic innervation mostly happens just around the atrium and around the SA node, AV node, whereas sympathetic kind of occurs everywhere. And then as a bit of a side note, usually athletes who train quite a bit, their resting heart rate is going to be reduced because their body sort of adapted. It's going to be able to pump out more cardiac output with every single beat, which means they require less heart rate to be able to achieve the same amount of blood flow. So they have reduced resting heart rate, but their peak heart rate is generally not affected. And this is because for anyone, you have a certain maximum amount of heart rate you can achieve to be able to get blood to the different parts of your body. If your peak heart rate is too fast, that means that your ventricle is not going to be able to fill up effectively, and you're not going to get blood flow to the rest of your body. So there's a specific sort of maximum you can reach with your heart rate, but generally for the resting heart rate, it will be reduced for athletes. So if anytime you see graphs, like if they give it to an exam and it shows one person with a resting heart rate that's like half of the another person, then you might think either obviously something might be wrong with them, but they could also just be athletes. Which is why when you are in clinical skills and you see the average of like 60 to 100 beats per minute is like normal, and then you go into the clinical setting and you see someone with 50, like when it's written in an exam, it might seem, oh crap, something's wrong with them. But 50 could just be like the person sitting in front of you is a elite athlete, and therefore their resting heart rate is just lower than the average person. So anytime you want to think about, am I a good enough athlete or not, you can always just measure your resting heart rate and see, is it 50? Is it 40? If it's 30, I might be a bit concerned. But yeah, like the lower your heart rate, the better you are probably as an athlete. Okay, and that's it. I'll pass it on to Jainul to discuss. So we discussed how cardiac muscles contract, but what actually signals them to contract? That's going to be what Jainul discusses. And again, if you have any questions, please let me know in the chat.
Thank you. I'll just share my screen so we can get started. All right, so is that visible for everyone? Yep, perfect. So we're going to talk about electrical activity of the heart today. So a quick disclaimer as well, we have covered a lot of cardiac physiology today. One thing we haven't covered, which you'll be covering in your lectures, is talking about how there's pacemaker cells in your heart and also cardiomyocytes which are contracting. So again, that'll be covered in your lectures, but I'll just explain it in very brief terms. Essentially in your heart, you have two types of cells. Ones that actually contract and pump and actually produce, the movements of the heart, which allow it to pump blood out of it. And it's also this separate type of cell called a pacemaker cell, which is able to generate its own action potentials and therefore create the rhythm or the beat of the heart. And we're going to be focusing more on that second type because that's going to play an important role in the rhythm of the heart. And we'll cover how that conducting system controls the contracting system. So in terms of more resources, at the bottom of our slides, I've also linked a couple of other PSPs who've made really, really great slides for that, but we'll just get started with the content. So first up, we have the conducting system. So like I said before, we have two types of cells in our heart. This type that we're talking about here is the autorhythmic cells or the pacemaker cells that are able to generate their own action potentials and spread them out to neighboring cardiac myocytes. So the way that it works is that these autorhythmic cells, pacemaker cells, are able to generate their own action potentials and they spread them out using gap junctions. And that allows it to reach neighboring cardiomyocytes and just sort of pass out in sort of a wave fashion. And the thing with these pacemaker cells is there's sort of all sorts of them located throughout the heart. You can see over here on the right, there's the SA node. Let me see if I can get a pointer up. So there's the SA node over here. There's the AV node, and there's a left and right bundle branches. There's a bunch of different autorhythmic cells or pacemaker cells in your heart. And they all are beating at different rates or firing pulses at different rates. What happens is that when this occurs, when you have all these different conflicting pacemaker cells, the loudest one or the one that's got the highest rate is going to become dominant. And that's going to set the rate for the rest of the pacemaker cells. So think of it sort of as like a sort of the loudest drummer amongst all the other musicians there. And that's the one that's going to become the dominant pacemaker or the dominant beat setter for the heart. A very small thing to also keep in mind is that we've talked about the SA node, the AV node, the left and right bundle branches, the bundle of hairs, the Purkinje fibers as well. It's also kind of important to know relatively where they're located. So with the SA node and the AV node, they're located in the posterior aspect of the heart, so the posterior wall, with the SA node being located just under the superior vena cava opening, and the AV node located under the tricuspid valve. Just keep that in mind because they can ask you about that either in exams or in specimens or in imaging. It's just important to know relatively where they are, but also understand the way that this circuit is connected and that pulses go from the SA node to the AV node, then down these branches and out to the ventricles. We're going to be covering that as well in the next slide, but just a little bit of an introduction to that there. And here is their actual conduction pathway. So we covered the actual individual nodes, but now we're going to talk about how those nodes are hooked up and then how the signal from the dominant SA node, the one at the top there, which is beating the fastest, how that dominant pulse is transmitted to the rest of the heart. So if you look over here, there's two pathways. There's the interatrial pathway and the internodal pathways. So as the name suggests, the interatrial pathway will allow the SA node to send out pulses to the atria, the top two chambers in the heart, or the superior chambers in the heart. And the way it does that is through this specialized conduction pathway called Bachmann's bundle. I'm not sure how you pronounce that, but Bachmann's bundle, however you want to pronounce it. And that allows it to go from the SA node, which is in the right atrium, out to the left atrium as well. Why is that important? Well, you want those atria contracting in unison to pump blood into the ventricles, right? So the interatrial pathway is very, very important to allow those atria to contract together. And then the second pathway we have is the internodal pathway. And that's a separate pathway, which is also very important because it allows the ventricles to contract. But the important part here isn't that the ventricles are contracting, but that they're contracting after the atria have contracted. So that you have a separation between atria contracting, therefore pushing blood into the ventricles, and then ventricles contracting and pushing blood out of the great vessels. So the internodal pathway is a second pathway that allows for that to occur. That's where the AV node is sending out these pulses at 60 to 100 beats per minute, but then it travels through the AV node. So it travels through the node over here. So it goes from the SA node to the AV node. Now, a special thing about the AV node is that it actually slows down the pulse slightly. And what that means is that as it travels through the AV node, slow down. Why is it important? Because if you slow down the pulse, you can then allow the ventricles to beat at a later time to the atria. So you're separating those two contractions of atria and ventricles. So it goes through the AV node or the atrioventricular node and down the bundle of His into the right and left bundle branches, and then up the Purkinje fibers of to the ventricles and the rest of the cardiomyocytes there. You can see the sort of diagrams that show that a lot more clearly, but an important sort of thing to keep in mind is how this wave of contraction is spread. So again, refresher over here on the diagram, you can see it all starts off at the SA node because that's the dominant pacemaker. Then it travels out via specialized conduction pathways to the atria, so the interatrial pathway. So the atria both contract, and you can see over here that they're both contracting in image number 3. But then those signals also travel via the AV node and go down into the ventricles as well. Now, one thing you might be wondering is why does the signals travel through the AV node, not like the nearby parts over here? So why doesn't it just go down here or from here down to here? Well, the reason is there's a bit of fibrous tissue between the two chambers of the heart that prevent the electrical signal just going straight down vertically from atria to ventricle, So it has to travel through the AV node, which is the only conduction pathway that allows it to actually travel through, which is why you achieve that separation of contraction between atria and ventricles. And here are 2 other diagrams showing the exact same thing. So you have the SA node, the AV node, and then down to the ventricles, Bachmann's bundle, all that there. And you can see another diagram here showing how you achieve that separation, where when the SA node contracts, pretty much soon after, that signal has reached the left atrium as well. And also it reaches the ventricles a bit later with that time period. Okay, so now we'll talk about the autonomic innervation. We've already covered that a bit in our previous section, but this is sort of a bit more of an anatomical look at it. So it's important to keep in mind where these nerves are coming from and what they're doing. So because your heart is composed of smooth muscle, it's going to require autonomic innervation to control it, right? You can't voluntarily control your heart rate or the way your heart's beating. That's all governed by autonomics. And so the innervation for, again, autonomics is going to have 2 components, a sympathetic component and a parasympathetic component. The sympathetic component is going to originate at the T1 to T5 roots in the intermediolateral cell columns. I think that's what it's called, the IMLCCs. And that's where the cell body will start. Then it will head out to the sympathetic ganglia and travel up and essentially reach the heart via the cardiac plexus. And you can see on the diagram on the right here, which shows that the nerve root starting off T1 to T5 and then heading off and going to the heart and innervating it, right? And it's also important to keep in mind, which you've already covered before, but it's also important to keep in mind the neurotransmitters and the receptors that are actually governing all this whole process. So what's happening is the sympathetic nerves are releasing noradrenaline, which are then acting on beta-1 adrenergic receptors of the heart. And the effect of all this is that it increases the cardiomyocyte contraction force. So there's more stroke volume because the cardiomyocytes are contracting more strongly, and therefore you're pumping out more blood as a result, so more stroke volume. And the second thing it's doing, which is also very important, is it's increasing heart rate as well. By acting on the sinoatrial nodes and the atrioventricular nodes, it's increasing the frequency that they're firing out action potentials at. So you're getting a bit of an increased heart rate as well, which we call tachycardia. And the second component of the autonomics is the parasympathetic nervous system. Now that's sort of governed by the vagal nerve or cranial nerve 10. And the way that this sort of originates is sort of in the brainstem, sort of in the brain, and then it comes down and it innervates the heart through this, through both the SA node and the AV node, allowing it to lower the heart rate at both these areas. And so it can actually have the opposite effect, the sympathetic nervous system, and lower the heart rate. And so when you're in sort of fight and flight mode, sympathetic nervous system is activated, you get an increased heart rate. And that makes sense because you want to have more blood pumping around to your muscles so that you can mobilize yourself and run away potentially, or fight the threat if you want to. And when you're in rest and digest mode, then you're going to be, at rest, you're not having any threat there. Your blood doesn't have to be, or your heart doesn't have to be pumping as hard to deliver blood to your muscles. And instead, it can be more relaxed and work at a slower pace. All right. I think it's a bit frozen. Am I frozen for you guys? Nope. Okay, so I think my slides are, oh, there it is. Okay. So the next point that I wanted to raise was that if you look back on the previous slides, we said that the SA node fires at a rate of 60 to 100 beats per minute. But when I actually measure someone's pulse normally at rest, then you'll find when you measure someone's pulse at rest, normally you'll find that it's much lower than that. Well, not much lower, but lower than that, right? It's going to be less than 100. And the reason is at rest, when we're normally just sitting here without doing anything, without any threat in front of us, without any stress, you're going to be in rest or digest mode, right? So normally your heart has a parasympathetic tone, which keeps your heart rate relatively low at about 60 to 100 beats per minute. It's not going to be very high, right? It's only when you're under stress that your sympathetic nervous system kicks in and actually elevates your heart rate to deal with that stress. For example, your end of year exams, which might be a bit of a stress for all of us here. And in terms of clinical correlates for all this stuff, I know a lot of this stuff seems like a bit confusing in terms of how you can link it up with an actual patient's pathology. But there are a couple of things that you can keep in mind, which are actually going to become much more important when we look at ECGs later on. But there's a couple of pathologies that are related to the electrical conduction system of the heart, specifically deficits in it and how that affects the rhythm of your heartbeat. So there's sinus, brady, and tachycardia, which basically means you have a either low or a high resting heart rate. And the reasons for that could be that the SA node is either firing too fast or too slow. But keep in mind again that we've already covered this with the previous section, but it's actually normal for athletes to have resting bradycardia. But of course, when they go into exercise, and when anyone goes into exercise, because we need the extra oxygen to our muscles, we're automatically going to go on tachycardia to try and deal with that stress. And another pathology to keep in mind is with the heart, there's a thing called heart block or AV block. So we said that the SA node fires, then it travels through the AV node, then goes to the rest of the branches. Well, if the SA node is sort of delaying those pulses being traveling across it, or even just blocking it altogether, what can happen is that the atria are firing at a different rate to the ventricles because the atria are being governed by the SA node, whereas the ventricles are being controlled by the slower Purkinje fibers or other sort of pacemaker cells. And so you're going to have this atria, which are contracting at a normal pace, but then the ventricles are contracting at a slower pace, which is what heart block is. You also have ectopics over here. So that's basically where you have pacemaker cells from other locations. So for example, rather than in the right atrium where you have the SA node, you might actually have other pacemaker cells in the left atrium starting to fire. And if they become loud enough and noisy enough, so dominant enough, they can actually become ectopic foci that actually drive the heart rate instead of the SA node, which normally does it. And that's something you'll be covering later on as well with pathologies as we talk about ECGs and how to actually figure out how we can actually observe this on ECG charts. So that's it for my section, and I'll pass it on to our next speaker.
Thank you, Jenna. I'll just share my screen. So, can you guys see my screen?
Yep.
All right. So now we're gonna talk about examination of back and spine. And my apologies, like last night we had a massive storm and the electricity is cut since then, so you might not be able to see me. As the examination of back and spine is has the same general principles as an examination of musculoskeletal system. So we have ask, look, feel, move and measure. Then if there are special tests, and lastly compare. So we're gonna start by discussing the examination of the cervical spine. So we're gonna start by an introduction. So you firstly introduce yourself to patient, explain what you are going to do and why you are doing it, and then discuss the required exposure for the patient and obtain the consent from them. So a proper exposure for back examination to fully expose the neck, shoulders, and arms, and probably ask the patient just to stay in their underpants. And one important thing is hand hygiene before the examination. Then we move to look. So you start with general inspection, looking for if the patient feels any pain or uncomfortable, any muscle wasting, spasm, swelling, any posture or scars on the skin, any deformities and spontaneous movements. Then we move to feel. So the position of the patient when where they will be sitting in chair or in prone position, so sleeping on their chest. First of all, you need to identify C2, C6, and C7. And so by running your hands down the cervical spine and feeling the spinous processes, the first like projection is C2, and then when you move down the spine, C6 is usually palpable but disappearing when, if the patient extend their neck, and then C7 is also easily palpable, fixed prominence at the base of the neck. Then you also feel the spinous processes, and intervertebral spaces, base joints, temperature, tenderness, and bony swellings. So when feeling the spinous processes themselves, also the disc space between the vertebra, the face joints are palpable approximately 2 to 3 centimeters lateral to the spinous processes, and press your fingers gently along these areas on both sides to detect any tenderness. Then move. So we have 6 neck movements. First of all, we have flexion, where you ask your patient to flex their chin onto their chest for 45 degrees. Then extension, extending, asking them to look up and back, also 45 degrees. We have lateral bending to either sides. So you can ask them to touch their shoulder with their ear and final rotation also to either sides. You may ask them to look over their shoulder to the left and right. Then we'll examine, we'll move to thoracolumbar spine. So when examining the lumbar or thoracic spine, you ask patient to stand or to sit if you want to examine the thoracic spine, with their arms folded across their chest. And as we said before, expose patient clothed in underpants only. So again, look for any posture, kyphosis, lordosis, or scoliosis. Look for any scars or abnormalities in the skin, and then muscle spasm or wasting, including buttocks. And then feel for spinous processes, disc or interferal space, face joints, tenderness, or any anatomy landmarks. So you need to identify T2 superior angle scapula and T7 inferior angle of scapula. And then the L4 and L5 landmark is very important, once as it's a safe access to the cerebrospinal fluid in the procedure of lumbar puncture. Then move. We also have 4 or 6 movements. So we have flexion, extension, lateral flexion to either sides, and rotation to either sides. Extension. The normal extension is to from 20 to 30 degrees. Flexion, normal flexions from 75 to 90 degrees. Lateral flexion, left, then right, and finally rotation, where the patient sitting and just each side by getting the patient to twist around while you stabilize the pelvis. Finally, we have the special tests. So we have firstly Schober's test, and this test, you first need to identify the position of the posterior superior iliac spine, and then mark a midline with a pen, as we can see here. Then mark 5 centimeters below this line and 10 centimeters above this line. And then ask the patient to bend forward in full lumbar flexion and measure the distance between these 2 lines. So the distance should increase by 5 centimeters at least. And reduced range of motion can indicate limitation in lumbar flexion. Another test that called nerve stretch tests, which are used to detect nerve root rotation, usually due to prolapsed lumbar disc. First of all, we have straight leg raising test, where you ask the patient to lying supine, keep the patient's heel on your hand, passively elevates each of the patient's legs in turn, and keep the knee extended. Flex at the hip to an angle of 90 degrees possible. So the normal test that there is no pain until 90 degrees of hip flexion with the knee straight. And if the patient feels any pain, you should stop the test. So criteria for positive tests: radicular pain that extends below the knee at 30 to 70 degrees in an L4 to S2 root or sciatic nerve, distribution in response to raising the extended leg, and or pain is relieved by knee flexion, or pain is aggravated by dorsiflexion of foot, which will be progress. So this is how you perform this test. And then we have Bragart's test. So it's the same as the previous test, but in this test, you will dorsiflex the patient's ankle, foot, and the test will be positive if the pain is reproduced. And finally, we have cross-straight leg raise test. So this is different from straight leg raise test because it has higher specificity than straight leg raising test for diagnosing lumbosacral radiculopathy. It's performed by raising the unaffected or symptomatic leg in a similar manner to the straight leg test. Look for the reproduction of radicular pain with the elevation of the opposite symptomatic leg. And the test will be positive if raising the extended symptomatic limb reproduces symptoms on the symptomatic side. And finally, conclusion, where you thank the patient and ask them to dress. Then you provide a brief summary of the examination findings, and finally hand IE after you finish everything. And that's it. I'll hand it over to the next presenter.
Sweet. I'll pull up the slides. Hopefully this works. Oh, nearly crashed. Perfect. Good start. All right. So we're doing normal aging. Oh, let's try and move that so it doesn't block everything. There we go. Normal aging. And that's not right. Okay, my slides have been messed up. Give me a tick. Alrighty. That slide is in the wrong spot. There we go. Fix that. Alrighty. The aging population. Okay, so aging is a time-dependent process of physiological change, which is progressive, universal, and species-specific and intrinsic. Aging comes with age-related diseases, and because of that, most people aren't able to achieve the maximum lifespan possible, which is one that is free of disease, as many of us are susceptible to them as we age. In terms of some statistics, the aging population makes up a large portion of our population now, which is only going to increase as time progresses. Right now in Australia, about 16.4% of the population is above 65 years of age. I think, if I remember correctly, that's about 4.5 million, so quite a huge percentage. Luckily for us right now, the life expectancy in Australia is quite high at 82.75, with females having a higher life expectancy than males, with females at around, I think, if I remember correctly, about 85.4 and males at 81 years of age, one of the highest in the developed world. In terms of this, with a growing aging population, there is more demands on the health system, and due to better treatment, we're able to prolong these the elderly's lives for longer, as well as this, but that also incurs many more costs, especially with a declining workforce, as we can see in this population period on the right-hand side. We have a top-heavy distribution, so the smaller workforce has to bear the grunt of the aging population. And one of the means in which the government is trying to reduce the demands of this aging population is getting them to work longer by preventing them from having access to the pension by increasing the working age from what it used to be, I think it was 65, and since 2017 has been slowly creeping up closer and closer to 67. I think right now it's at about 66 years and 6 months. And by 2023, it will be at 67 years of age. All right, and as such, with aging, comes the consequences of aging. And there are increased susceptibility to disease, and changes in physiology. And the elderly are more prone to a cascade of itogenesis, which is a sequence of related adverse events triggered by initial medical intervention. An example of this would be an elderly patient. If they fall, like if they were young, they probably would just get up and there won't be any problems. However, as being old, you're more frail, your bones are weaker due to osteoporosis and decreased muscle strength. You're more likely to get a hip fracture. As you're older, your immune system's weakened, therefore your recovery time is longer and the chances of infection are higher. Once this infection takes place, you're more likely to require antibiotics to clear the infection. That may result in you requiring antibiotics, and due to being older, your renal function is decreased, so you're more likely to get renal damage from the antibiotics due to toxicity, and basically you see this cascade of adverse effects that may result in death. As such, on top of that, you get altered presentations of diseases in older people, such as due to the blunted immune system, you're more likely not to get that fever response with many of the infections they might get. It's only when the infection is very severe, you'll see that fever. And you get altered drug interactions because of decreased liver and renal processing ability. Moving along, in the next few slides, it's just going to be a big table of the changes that are present and management and complications of it. I'll be just giving a brief skim of this because it's very detailed, not something you need to know too specifically, and it's just, if you really want to know it, you can look at the slides. So in terms of cardiovascular changes, you get reduced contractility and compliance of the heart. This is due to increased fibrous tissue of the myocardium, which is the heart muscle, so they're not able to contract as well. And also you get arterial stiffening and reduced electrical conductivity of the heart. That is due to decreased pacemaker cells being present in the SA and AV nodes. So your heart is less able to contract and push blood around the body. And because of that, you get significant other problems that can occur, such as heart failure. You get greater risk of arrhythmias and increased orthostatic hypertension. In terms of neurological changes, with increased age, you get less neurons within your brain, as well as increased degeneration of neurons. And then you get decreased cognitive function due to the reduced number of nerve cells and the ability to create new neural connections. So you may see reduced functions in working memory, execution function, processing speeds, attention span, and learning new information. This is normal with aging. However, when it gets to a certain degree that is severe, it can be classified as dementia. And basically, also to this, patients often experience reduced balance and increased risk of delirium. So in terms of complications, we want to manage elderly patients for risk of falls because of their reduced balance. In terms of musculoskeletal changes, as you age, you get significant reductions in the mass and strength of your muscles because you get wasting. And in terms of your bone, because of age, you get osteoporosis or bone density loss. And that's why you want to be super careful when it comes to falls, as one fall that would usually just result in a bruise may turn into a fracture, and that has many knock-on effects for the patient. In terms of respiratory changes, as you age, your parenchymal tissue reduces in elasticity, which is your lung tissue. So your body is less able to exchange gases. You have a reduced endurance of your muscles. So patients often present with increased rate of breathing because their lungs are not as able to exchange gas as they used to be. And basically, in terms of management for this, it's when an elderly person comes in with shortness of breath or difficulty breathing, we're more liberal with the use of oxygen. In terms of the renal and genitourinary changes, with age, as we saw before, we get muscular muscle weakening. And because of that, you get symptoms such as increased urinary incontinence because you have weaker pelvic floor muscles, and the ability for your bladder, which is actually a muscle, a muscular sac that squeezes to push out urine, that muscle becomes weaker. So you have decreased bladder capacity, as well as the inability to completely empty the bladder. Additionally, in terms of the renal system, you get loss of glomeruli, reduced filtration units within your kidneys or the nephrons. And because of that, you're less able to maintain homeostasis in terms of water balance, electrolytes, and renaling processing of drugs. That's why in terms of management, you got to be careful with adjusting your drug dosages, as clearance is a lot lower and slower in elderly patients. In terms of gastrointestinal changes, there's no significant changes in absorption. However, with the stomach, we get decreased prostaglandin synthesis, delayed gastric emptying, and impaired microcirculation. That's why you often see elderly people getting fuller faster and feeling like they're fuller for they don't eat as much as compared to younger people. Also, you get increased constipation. So you want to be wary of drugs that increase constipation when given and administered. In terms of the skin and hematological changes, skin, we get increased thinning and reduced vascularity, dryness, and sun damage is more common. And because of that, you're more likely to get pressure wounds from excessive sitting or lying continuous pressure in a certain area. In terms of your blood, you're more likely to have a blunted immune response due to your weakened immune system. And as said before, you're less likely to have inflammation from or a fever response because your blood cells are less likely to be more reactive to pathogens compared to when your immune system was stronger. Homeostatic and immunological changes. In terms of homeostasis, as your body is less, basically all the bodily systems in your body have become weaker, you're less able to maintain homeostasis. Therefore, our older people are less able to cope in extreme weather conditions or with dehydration or fluid balances. And as noted before, poorer immune systems. Sensory changes, again, with degeneration of cells and weaker cells and so on and so forth, you get vision changes. So you're more sensitive to glare, you get degeneration, and from that degeneration, you get decline in contrast sensitivity, as well as hearing. And because of this, you get increased likelihood of falls, and it makes communication more challenging in terms of hearing. And smell and taste are diminished, so it could also influence the appetite and may lead to malnutrition in the elderly. And with those with those conditions or those physiological changes, patients may experience decreased ability to function, and this may affect their mental state, resulting in things such as depression, anxiety, and as well as with the degeneration of nerve cells, you may see dementia and delirium in elderly patients. Frailty is a biological syndrome of decreased reserve and resistance to stresses resulting from cumulative declines across multiple physiological systems and causing vulnerability to adverse outcomes. Basically, there's a direct correlation between the more frail a person is, the more likely they're going to have adverse medical conditions once a challenge occurs, such as a fall or most likely a fall leading to a cascade of iatrogenic effects. And basically there's two scales, the Fried's phenotype scale and the Rockpool's frailty scale. And basically it's the more frail the person is, the more likely they are likely to have they are more likely to end up having death, end up dying due to the cascade of effects. All right, moving on, we're doing the elderly, death and dying. First of all, we're going with the definition of death, and basically the Australian definition of that is the irreversible cessation of all circulation in the body or irreversible cessation of all functions of the brain or brain dead. Irreversible coma, loss of brainstem response and respiratory center functions. And basically how that is determined is on the right-hand side. Here's a list of tests that doctors perform or you may perform once in the future. And you get one of those cool movie moments where you get to say the patient has died at some certain time, so on and so forth. And basically there's a whole range of tests to test those reflexes or those not the reflexes not being present as such. Factors involved in the experience of death and dying, the type of death. So is it sudden and unexpected, so such as in a stroke or MI, sudden expected, such as a patient undergoing a chronic disease such as cancer, and sudden and expected, so acute event of a chronic disease such as a cardiac arrest, or expected and prolonged, such as in a cancer. The age of the patient, the younger, it's harder to understand and more difficult. Cultural factors and religion, as more spiritual people are able to cope with death and the idea of dying better. And as such, they have, due to that, because they have greater mental health and coping mechanisms, so they're able to understand and accept death better than those who don't have those support networks, as well as having previous encounters of death and dying. The definition of a good death is highly debated. There's both an individual perspective as well as a professional perspective. In terms of the individual perspective, it's a balance between the quantity versus the quality, having the freedom of being free from the pains and symptoms, access to being able to die a dignified death. What that is very dependent on the own person's perspective. Whilst in terms of the clinical aspect, it's just having the symptoms controlled and acceptance of the outcome. The stages of dying are that of denial, anger, bargaining, depression, and acceptance. Denial is such as, why is not me, as if it's not happening. Anger is, why me, and being angry at the situation. Bargaining is trying to understand, trying to bargain basically of why it's me and not somebody else, and why it's now as opposed to later. And then there's depression and acceptance. But however, this model that was created in the 1960s does not include the other emotions which are commonly experienced with death, such as fear, hope, shock, anxiety, and so on. Next is how to recognize if someone is dying. This often comes under the idea of the surprise question. Would I be surprised? That you should ask yourself, would I be surprised if this patient died in the next year? If yes, they're most likely not going to die. If no, they're likely to, you can recognize that they probably are dying. However, this is very arbitrary. So there are systems in place that help you with coming to this conclusion, such as the supported and palliative care indicator. And basically 2 or more of these being ticked off suggests that there is deteriorating health and increased mortality. So in terms of caring for a dying patient, apart from the clinical aspect where you're just trying to alleviate pain and looking at the symptoms and trying to find treatment options, you also have to understand there's a cultural aspect to it. As always, don't assume, always ask. As with many patients, they may turn to religion, even though in the past they may not be a religious person when dying, as it helps them cope with the situation. And you want to cultural value, cultural religion that they may have, such as in Buddhism, attendance in the instance of death, they want attendance of that patient's death to be quiet, as it provides a calm setting for the mind. Yeah, and then not to be disturbed, as well as opposed to other cultures where the bereavement and grieving, this is an important step in recovering from somebody's death, and it's important for both the patient themselves to understand what is happening to them, as well as the families and friends to be able to move on and move past losing somebody really important to them. And there's two types of grief. There's the anticipatory grieving, which is grieving as you know the end is imminent, as well as morbid grief, which is when the grief goes on for too long and without development of changes. So this is when it becomes an issue, when it's too severe compared to the situation at hand. And this often spirals into psychological problems such as depression and so on. And basically, there are certain factors involved that increase the chances of morbid grief, which is that if the death is of a younger person, if a person has lack of social support, and if the patient already has underlying mental, physical health problems. Once death has occurred, the procedure that follows is that the death is certified by a doctor, the family is notified, a death certificate is completed, and a funeral is arranged. However, if an autopsy can be arranged if the patient's family wants to, or if there's any malpractice that has occurred or is reported to the coroner as listed below, but it must be done within 14 days of the death. Advanced care planning is also relevant in this case due to the with dying, as it gives a directive to the loved ones of a patient if their cognitive function declines. And with advanced care directives, there are two directives: the instructional directive and the values directive. In terms of the instructional ones, you can think of that as the do not resuscitate order. So a patient saying, if I was to have a cardiac arrest or respiratory failure, don't bring me back from the death. Whilst the values directive is more of just a patient's values and preferences in life, and it's up to the discretion of both the family and the doctor on how to follow that. Moving along. Again, then there's voluntary assisted dying, which is legal in Victoria and most of the states in Australia. And basically, it's a decision where patients who are experiencing an advanced progressive disease can end their own life under the guidance of a medical practitioner with the injection of a lethal dose. And basically, who can access this are Australians and citizens in permanent residences, and they must be of age 18 and up, and have decision-making capacity when doing so, and they must be diagnosed with an incurable disease. And basically, because it's death, there's a very stringent process that a patient must get through before they're able to take their own life, and that is that two doctors must approve of this, and then the request must be confirmed by the patients 3 times, once in an initial request, then a written one, and then a final verbal request. And that's it for me.
Awesome. I think that pretty much wraps us up for today. So if you have any questions, feel free to stick around. Otherwise, thank you for coming and have a good week.